In our third learning objective, we're going to be developing an understanding of effective nuclear charge. And we're going to see the role that effective nuclear charge has in the size of the atoms or size of ions. To understand effective nuclear charge, we must begin by understanding shielding. Here's the definition. The effect in which electrons can reduce the electrostatic attraction between the protons of the nucleus and other electrons. So what we are considering here is we have a nucleus, and we know that in this nucleus there are protons. There's neutrons as well, but that nucleus has got a charge. And we have electrons that are being attracted to those protons. That attraction is opposite charges, and it's called an electrostatic attraction. Shielding is an ability for electrons to block a little bit the field of that outer electron from the nucleus. And that's what shielding is, the effect in which electrons can reduce the electrostatic attraction. So with the idea of shielding, we can now define effective nuclear charge. It's the nuclear charge felt by an electron. Okay, so it is that electrostatic attraction, but it's not going to feel necessarily the full positive charge of the nucleus because of the shielding effect. So the effective nuclear charge will be the actual nuclear charge. Okay, so that would be the number of protons in the nucleus. That's its nuclear charge. And then this sigma that we see here is a symbol for shielding. So the shielding by other electrons, keeping from an electron that we're interested in from filling that nucleus. So each electron has an effective nuclear charge, what it senses that nucleus as being. The stronger that effective nuclear charge, the more tightly the electron will be held onto that nucleus. The lower that effective nuclear charge, the further away that electron will be from the nucleus because it's not getting the same tug from that electrostatic attraction. So what kind of shielding are there? There are basically three degrees of shielding that we're going to look at. The first one is electrons are shielded very effectively by electrons in subshells that are closer to the nucleus. So if we redraw the picture that I had drawn earlier where we had the protons in the nucleus and we had an electron out here, if we have an electron between this electron and its nucleus, this electron here is very effective at shielding the outer electron from the nucleus. If you have an electron that's in the same shell, okay, so it's the same relative distance. So let's put an electron here. This electron is competing for the positive charge of the nucleus with this electron is competing with this electron. So there's a little bit of shielding, but not extensively. This one certainly would do it a lot more because it's between the outer electron that we're considering and the nucleus. Now, if there were an electron sitting way out here, this one would not be effective at all at shielding this electron from its nucleus. Okay, so outer electrons beyond the one that we're interested in don't shield. So what does this have to do with anything? Why do we care about effective nuclear charge? Why do we care about shielding? Well, the reason is we can use this to learn trends in atomic radius and then eventually in ionic radius. How do we define atomic radius? Well, we know what a radius is. A radius would be the distance from the nucleus to the outside of this circle. However, you can't determine where the outside of that circle is very well. Take our half the distance between two nuclei. It's very easy to find nuclei. We've got means by which we can do that. So if we look at this nucleus and determine the distance between that nucleus, cut it in half, we can assume that that would be the atomic radius. If we had a diatomic molecule, like maybe this was Cl2, again, we would assume that these two are bumping up next to each other, and we would define the atomic radius as 1/2 the distance between those 2 nuclei. So that's how it's defined. Now let's see how effective nuclear charge and shielding define the size of the atom. Now before we do that, I want you to understand that it is never an issue of crowding, where because you have more electrons, you need more space for them to move about in. Remember when we talked about the relative size of the nucleus versus the size of the atom, and we said to imagine that a marble was suspended in the middle of a big football stadium or soccer stadium, and we had that marble suspended above the 50-yard line. The rest of that stadium would be the size of the atom. Electrons are way tinier than the nucleus, and they're moving about in that space of the rest of the stadium. It's never going to be a crowding issue. What defines the size of these atoms is going to be the attractive force that the nucleus is pulling on those electrons. The more those outer electrons are feeling that nuclear charge, the higher that effective nuclear charge, the tighter it's going to draw those electrons in. The lower that effective nuclear charge, the bigger the atom is going to be. So never think, well, I've got more electrons, therefore it has to be bigger. That's not the argument. It is the attractive force that those electrons are feeling that nuclear charge, okay? Effective nuclear charge. So let's consider 2 atoms here. I have on the left an atom of lithium. Okay, with this atom of lithium, I want to consider this outer electron right here and what it is feeling that nuclear charge as. Now we know the nuclear charge is a full +3, but it's not going to feel that full +3 because it has 2 electrons between it. So these are in the 1s orbital. This is in the 2s orbital. We know the 2s is further away, and those 1s can shield it effectively from the nucleus. Now we can use as a rough estimate of shielding, works pretty well for our arguments, just how many electrons are between that outer shell and the nucleus. Okay, so we have got the effective nuclear charge being the nuclear charge minus the 2 electrons that stand in the way between the outer electron and the nucleus. So this number 2 is because of these 2 electrons. And that'll give me an effective nuclear charge of +1. So this electron that is sitting out here in the outer shell is going to feel a +1 pull. Now let's go to the next atom on the periodic table, which would be beryllium. Okay? In beryllium, we have 1 more electron, and therefore we have 1 more proton in the nucleus. So we have got 4 protons in the nucleus, and the nuclear charge would be 4. If we consider the pull of this electron, it's effectively being shielded by this electron and this electron. So there's being effectively shielded by only 2. Now this is a little bit of shielding, but not enough to really consider. So when we work on the effective nuclear charge of this, we see that we have a nuclear charge of 4 because there are 4 protons in the nucleus. The 2 is the shielding, okay, and that is coming from these 2 inner electrons, and that is going to give us an effective nuclear charge of +2. So if I were to consider again this electron right here, it is feeling a +2 pull by the nucleus. Now if it is feeling a +2 pull, an electrostatic attraction of a +2 with a -1, it is going to pull it in more tightly, and therefore the atomic radius of beryllium is going to be smaller. Now if we continue to work our way across the periodic table, as we work across the periodic table from lithium to beryllium to aluminum, and actually boron is next, and carbon and nitrogen. As we work our way across that periodic table, what is happening? We're continuing to add one proton into the nucleus. So as we go across the periodic table, this keeps going up. But we're continuing to add electrons into the same shell where n is equal to 2. We'll put them in the s, and then we'll put them in a p, but we're putting them all in the same general distance from the nucleus. Therefore, the shielding is not changing as we go across the periodic table. The shielding is staying at 2. So as we go across the periodic table, okay? Z keeps going up by 1. Keeps plus 1 as we go across. But the shielding is staying constant. And so the effective nuclear charge is going to keep on going up by 1. So what is that going to do to our size trends? Well, let's look at it. So here is just the representative elements, actually the main group elements represented, so we don't see the transition elements there. And we can see as we follow a group across, I mean not group, but a period across, that we see this decrease in size as we move across. Now there's some minor variations to that, but for the most part we see that decreasing occurring. So as the effective nuclear charge is going up because the shielding is staying constant across there, we see that decrease in size. Now all of these are measured in picometers, just so you know. All right, so we're adding a proton and electron as we go across. 1 proton, 1 electron. The shielding is not changing, so it keeps getting smaller and smaller. But what happens as we go from neon to the next element? It increases drastically in size. It goes from 70 picometers to 186 picometers. Now, what would cause that to happen? Well, let's consider what's happening between the neon and the sodium. In the neon, we have in the first shell 2 electrons. Okay, that would be the helium core. When we move out to the second shell, as we're moving across this period that we see here, we're putting our electrons in the second shell. Okay, so we're putting those electrons here until we get 8 valence electrons in that shell. And then the next one, for the sodium, it needs to move out to the third shell. So it is going into the 3, it'll be a 3s1 for that last electron. What happens? Well, this is the outer electron. What is suddenly happening to the shielding? We've gone from, for neon, a shielding equaling to 2, to sodium, where our shielding is the 2 electrons we see here, plus the 8 electrons that we see here, and so the shielding has just jumped to 10 versus the 2 that we had for the sodium. So suddenly there's lots more shielding, the effective nuclear charge drops down, and that means that sodium will be much larger. So the trend down of group is that it will increase in size because you're putting it out into the next available shell and increasing the amount of shielding that there are. So every one of those, without exception, is going to increase in size as you go down. So increasing size from right to left and from top to bottom on the periodic table. Here's another way of looking at that. And one of the things that we see here is that across the this area right here is going across the transition elements. And as we go across the transition elements, the size trend doesn't change very much. It is levels out quite a bit. And the reason for this is the electrons that you are placing as you go across the D are not being placed in an outer shell. They're being placed into an inner shell. Remember, for example, let's do titanium. The electron configuration is argon 4s2 3d2, and we're putting the electrons as we go into an inner shell. That's not the outer shell. That's not the outermost shell. The outermost shell is this. So as we go across the transition elements, we are increasing the nuclear charge by 1, but we're also continually increasing the shielding by 1. So we see a somewhat leveling out of the size as we go across those transition element areas. So that's our atomic radius. We know that for atoms, when you're comparing atoms, they get smaller as we go across the periodic table. They get larger as we move down the periodic table. Okay, it levels off somewhat across the transition elements, and that trend is the way it is and the way it's laid out because of the electronic structure of the atoms. I want you to not only know the trend, but understand the why behind the trend. Understand the shielding effect and the effective nuclear charge that defines those. Now let's move on to ionic radius. Okay, so an ionic radius would be just the radius of an anion or a cation. And in order to consider trends of these radii, let's start with cations and let us compare the metal to its cation. Okay, so we're going to start and we're going to consider lithium, the element, as an atom versus lithium, the cation. When you're comparing an atom to an ion and comparing their sizes, it's very helpful to look at the number of protons versus the number of electrons. So if we compare these two, we know that they both will certainly have the same number of protons. They both have 3 protons. However, lithium as an atom is going to have 3 electrons, but lithium as a cation is only going to have 2. We've removed 1 electron. So in this scenario, we have the same nuclear charge, okay? In this scenario, we've got 3 electrons being held on by those 3 protons, and here we only have 2 electrons being held on by those 3 protons. Plus, what did we remove? We removed a valence electron, so we are considering electrons that are on the inner shell, okay? So think about those things and answer the question, which one would have the larger radius? Well, if you picked lithium, the element, the atom, you would be correct. The atom is always going to be larger than the cation that you make from that atom because you are removing an electron and the nuclear charge is now being holding on to fewer electrons and can draw them in more tightly. Now, if we consider for anions, let's consider an atom versus its ion, and let's do it for fluorine versus the fluoride ion. So we'll construct a similar table here. The number of protons, as we go to the periodic table, we see that the atomic number is 9, so they both have 9 protons. For fluorine, the atom, it would have 9 electrons. For fluoride, the ion, it would have 10. So we have got 9 protons in both situations. Here the 9 protons is drawing in 9 electrons, attracting 9 electrons. This one is trying to hold on to 10 electrons, 1 more electron than the nuclear charge itself. So with that information, maybe you can think through which one would have the larger radius, the fluorine or the fluoride. If you chose the fluoride, you would be correct. And the truth of the matter is, every time you compare an atom to its anion, so you take a nonmetal and create an anion from it, the anion will always be larger than the atom itself. Now, just to show you a relative size change between the atoms and the ions, as we go from lithium to lithium plus, we know that that's decreasing in size. As we go from fluorine to fluoride, it is increasing in size. So by transferring 1 electron is coming from here and being placed on here, it makes a very big difference in the size of those ions. So we've looked at atom trends, we've looked at a comparison of an atom to its ion. Now let's compare the radii of ions and atoms in an isoelectronic series. Remember, if they are isoelectronic, that means they have the same electron configuration. To have the same electron configuration, they must have the same number of electrons. Now, once again, it's helpful to compare the relative number of protons and electrons when we do these isoelectronic series. Since they're isoelectronic, the number of electrons is not going to be changing, but the number of protons will. So we're going to look at a series of these 4 ions. We've got sulfur chloride, potassium ion, and calcium ion. And we'll work our way through a table again. So let's construct another table. Here we've got these 4 ions, and I did not put the noble gas that they are all isoelectronic with. Argon is somewhere in the middle there. But these are all isoelectronic with argon. They all will have an argon electron configuration. Now, if you go to the periodic table, you can determine the number of protons each of these will have. Okay, so we have 16, 17, 19, and 20 protons in each of these. Now in terms of electrons, let's start with sulfur 2 minus. Sulfur 2 minus, we gain 2 electrons over the number it had to begin with, which as an atom would be 16. So it's going to have 18. And as we do that for each one of these, we'll see that they all have 18. They're all isoelectronic with argon. Argon has 18. So you're going to consider these two questions. Number one, which ion would be the largest? And which ion would be the smallest? I want you to think about that, and you're going to be answering that question here in just a moment. But before I change to that question, what are you thinking about? You're thinking about the pull that the protons are going to have for the electrons. So it's drawing those electrons in. Which one do you think will be more effective at holding on to its 18 electrons? An atom that adds 16 electrons, or an atom that has 20 electrons. So the largest and the smallest is certainly going to be one end or the other. Let's see what you can do with this. Okay, so if you answer the question, did you choose number 4? Then you'd be correct. The largest one would be the one with the fewest number of protons, holding on to 18 electrons, and that was the sulfide. The smallest one would be the one that had the most protons holding on to those 18 electrons. So number 4 is the correct answer. Now this is just showing relative sizes of these ions, and I see students very often who will be asked to compare two things on the periodic table. Maybe they're going to compare potassium plus and Cl minus on their size, and these are isoelectronic, and so they'll say, okay, I know trends. Trends are they get smaller as we move to the top, they get smaller as we go across the periodic table. Therefore, since chlorine is further up and further to the right, it's going to be smaller. Well, that certainly is not the case, is it? It is larger. So the thing that you can't do is use the trends when you're comparing ions. Having said that, however, we can do a little bit of comparison. Let me erase everything I have on here, and let's focus on a family. If you're comparing the same charge for a group, okay, so we're looking at the halogens and we're looking at the halides, these ions. It got bigger as we went down the family or down the group when we were talking about atomic radius. If they all have the same charge, then that is also going to be true as we go down with its ions. Okay, so that trend does hold true when we're looking at the periodic table, no matter which group we choose. Okay, so this ends our learning objective number 3. We've talked about shielding, its role in effective nuclear charge. We've looked at effective nuclear charge role in atomic radius, and then we've compared ions to their atoms, and we've compared isoelectronic ions to each other in terms of their radius.